Doctors, seieu i descobriu-vos. Sigueu tots benvinguts a aquest acte acadèmic d'investidura del doctor Evert Hoek com a doctor honoris causa per la Universitat Politècnica de Catalunya. Una cordial salutació també per a aquells que esteu seguint aquest acte a través del canal UPC Televisió. M'acompanyen a la taula la secretària general de l'UPC, la senyora Marta de Blas, i el vicerector de Política Científica de l'UPC, el professor Gabriel Bugeda. El professor David Parcerissa serà el padrí del nou doctor honoris causa. Tinc l'honor d'obrir la sessió. La secretària general de la Universitat Politècnica de Catalunya, la senyora Marta de Blas, llegirà l'acte de nomenament del doctor Evert Hoek com a doctor honoris causa d'aquesta universitat.
Com a secretària general certifico que el 21 de juny de 2018 el Consell de Govern de la Universitat Politècnica de Catalunya, per mitjà de l'acord CG/2018/05/32, va aprovar nomenar doctor honoris causa de la UPC l'acadèmic Evert Hoek a proposta de l'Escola Politècnica Superior d'Enginyeria de Manresa. Avui, 7 de març de 2019, en aquesta cerimònia solemne que ens aplega, el rector de la UPC, Francesc Torres, que en farà la investidura, el padrí, David Parcerissa, que en farà la lloa, els doctors i doctores que formen el seguici que l'acompanya i tota la comunitat universitària, celebrem l'acte d'investidura com a doctor honoris causa d'Evert Hoek, acte amb el qual tenim l'honor que s'incorpori com a membre de la nostra universitat. D'ençà que es va graduar l'any 1956 a la Universitat de Cape Town, la seva trajectòria docent investigadora en el camp de la mecànica de les roques l'ha dut a diverses universitats del món, com l'Imperial College de Londres o la Universitat de Toronto, on ha estat professor. També a la Universitat de Waterloo, on ha rebut doctorats honorífics. Així mateix, l'han dut a les aules de la nostra universitat, on la seva contribució teòrica s'ha incorporat en nombroses assignatures, tant del grau com del màster en enginyeria de mines d'aquesta Escola d'Enginyeria de Manresa. Per tot això, és un honor, un orgull i un plaer celebrar aquest acte d'investidura del professor Evert Hoek com a doctor honoris causa de la Universitat Politècnica de Catalunya. It's an honor and a pleasure to be witness to all that and to be able to personally congratulate Professor Evert Hoek.
Gràcies. Professor Gabriel Bugeda, vicerector de Política Científica de la Universitat Politècnica de Catalunya, prego que vagi a buscar el doctor Evert Hoek. Gràcies. Prego al padrí, el professor David Parcerissa, que faci el laudatio dels mèrits del doctor Evert Hoek. Sisplau.
Dr. Hoek has dedicated his life to the study of how rock masses behave and break. In fact, almost every one of us has at some time, usually during their childhood, been interested in how things break. Even my daughter today is a specialist on that subject. The difference is that Dr. Hook persisted after his childhood and chose this interest as a way of life. Over a number of decades, civil and mining engineering projects have become more and more challenging as they have become bigger, deeper, heavier, taller. Thus, how dams and bridges are built, how slopes are stabilized, and how tunnels and caverns are excavated and supported have been completely transformed. At the same time, problems in rock mechanics have become bigger, deeper, heavier, and taller too. In 1972, in a paper entitled The Teaching of Rock Mechanics, Dr. Hook discussed the need to increase interest in rock mechanics. The author said that society's reaction to rock mechanics is very poor, and the most prevalent reasons were these. Reason 1. A mining and civil engineering company with a rock mechanics problem was unaware of the existence of the subject of rock mechanics. Reason 2. Having decided to investigate a problem, a company became completely disillusioned by the lack of practical solutions. And reason 3. Once the company was convinced that there were tangible financial benefits to be gained from the application of rock mechanics to its problems, there were relatively few companies that could provide a comprehensive service to satisfy this need. Currently, the presence of engineers specialized in rock mechanics is crucial in mining and civil engineering projects. An enormous pool of practical solutions has been developed during recent decades, and there are companies that are exclusively devoted to providing assistance in rock mechanics problems. The contributions made by Dr. Hook from the very beginning of his research in 1958 have contributed significantly to making changes that affect these three reasons and have had an essential impact on the way that rock mechanics problems are solved and the cost involved. Dr. Hook has produced numerous high-quality papers and textbooks. The book Rock Slope Engineering, which Dr. Hook wrote with Dr. Bray, the book Underground Excavations in Rock with Dr. Brown, and a third book, Support of Underground Excavations in Hard Rock, written with Dr. Kaiser and Dr. Bowden, have become Bibles for rock engineers. He has continued to update Hook's Corner in the Rock Science website, which is a valuable source of information too. Additionally, Dr. Hook and Dr. Brown developed the Hook-Brown Rock and Rock Mass Failure Criterion, whose use has become widespread in international rock engineering practice. Later, it was combined with the Geological Strength Index, also developed by Dr. Hook, to form an important tool in rock engineering and design. Recently, Dr. Hook and Dr. Brown co-authored a revision of both the Hook-Brown Failure Criterion and the Geological Strength Index, to be published in the Journal of Rock Mechanics and Geotechnical Engineering in 2019. As a consultant, Dr. Hook has given expert advice on a number of very important infrastructure and mining projects around the world, providing solutions to important issues and contributing to create safe work conditions. Over the last decades, Dr. Hook's achievements in rock design and rock engineering have been so paramount to our understanding and practical use that we must all be deeply grateful. Thank you.
Doctors, cobriu-vos. Anem a investir solemnement el doctor Evert Hoek com a doctor honoris causa per la nostra universitat. On behalf of the faculty of the Universitat Politècnica de Catalunya, in recognition of your outstanding achievements, I grant you an honorary doctorate. By the authority vested in me, I present you with this diploma. I also present you with this biretta, a revered emblem of the highest academic level. Wear it proudly as a symbol of your achievements. Receive the ring traditionally bestowed in this ancient ceremony as an emblem of the privilege of signing and sealing reports, consultations, and criticisms corresponding to our science and profession. Also receive these gloves, these white gloves, which signify that your hands must remain pure, and like the ring, are a symbol of your dignity. Henceforth, you shall form part of our university. Faculty, please receive a fraternal embrace from those who are honored to call you a colleague.
And associates and friends, thank you very much for this opportunity to address you on this auspicious occasion of my honorary doctorate degree. I originally graduated as a mechanical engineer from the University of Cape Town a long time ago, 1955. I obtained my bachelor's degree, and in 1958, my master's degree. I specialized for my master's degree in stress analysis and strength of materials. In those days, that was a vastly different subject from what it is today. There were no computers, none. There were no calculators. The tools that we had at our disposal were logarithmic tables, and if you were lucky, a slide rule, and that was it. So it took a long time to do the kind of analysis that we do today. One of the most powerful tools that we had at our disposal was a technique called photoelasticity, and if I can get it to work. I haven't been instructed on how to operate this machine. Okay, you'll change. This photograph shows a photoelastic stress pattern for a crane hook. Photoelasticity is a technique whereby you can view a stressed, transparent plastic material in polarized light And what you see there is can I go back to that one? Is a pattern showing the stresses in a crane hook supported in the top black dot and loaded by the lower dot. And what we can do is to analyze this to determine what shape it should be, what the stresses are, and whether the load carrying capacity is adequate. Obviously, if it's overloaded, as you can imagine, it will break across the center in bending. It's a very powerful technique, not used today because we can do all of this numerically now, but very important in those days and very tedious. It would take months to analyze all of the information in that kind of image. The next image is quite a different pattern. This is a glass model in which I have been studying the cracking of the roof and the floor. You can see cracks that have developed there in the glass, and with these types of models, let's move it much closer. There we go. With these types of models, one can examine the detailed progression of failure that is important for us to know in the design of underground mines and underground excavations. Today, we have computers that make this an entirely different process. The first calculator that I purchased was at Imperial College in about 1972. It was a little bit like this one, and it cost £500 sterling. It could add and subtract and multiply and divide, and that was it. And today, the other day, my wife and I were walking in Barcelona, and we saw a calculator, smaller than this, but similar, for €1. So the world has progressed a long way. And of course, with the development of computers that we are all familiar with, we carry in our pockets, in our supercomputers, in our cell phones, the world is a very different one. After I had graduated with this speciality, I was employed by the South African Council for Scientific and Industrial Research, which is a large organization that deals with all research work of all kinds across the whole field. And in particular, I worked for the National Mechanical Engineering Research Institute in South Africa. I should have mentioned earlier that I did my degrees at the University of Cape Town, although I was born in Zimbabwe, then Rhodesia, in 1933, so that I'm 85 years old this year. There were no universities in the country at the time, and so we had to leave the country, and I went to Cape Town. So in South Africa, I started my research and started it as a mechanical engineer. And the reason that I started studying rock was that it was a material of vital interest to the mining industry. At that time, mines were approaching 3 kilometers below surface in the gold mines in central South Africa. And there were problems that were called rock bursts, where the stresses were high enough that the rock literally exploded when it failed. And it was obviously a very dangerous environment in which to be. And so I was asked if I would study rock as an engineering material, and which I started naively thinking that it was like steel or concrete. I soon discovered that it's quite a different material, and I'll tell you a little bit about that as we proceed. In 1966, I was appointed to a readership and later to a full professorship at Imperial College of Science and Technology, which, rather like the UPC arrangement, the University of London has 26 colleges scattered around the City of London. One of those colleges is Imperial College of Science and Technology, and one of the schools in the college is the Royal School of Mines. And so I was a professor in the Royal School of Mines, which approximately is analogous to the School of Mines here in Manresa. And I very quickly realized that I had to expand beyond looking at rock, pieces of rock of this kind, where you're looking at intact material from, this is a drill core that was lent to me by Professor David Processor. And I had to expand to look at rock in a broader sense, because rock in general is a very inhomogeneous material. Even on this scale, you have mineral grains of different composition cemented together, and quite randomly, so it's not a predictable material. And then when it's subjected to tectonic deformation due to plate movements and mountain building processes, as you have here in the Pyrenees and behind them in the Alps, the rock is broken into interlocking blocks of material, and its behavior becomes very complicated. So that the problem we face in rock engineering is, how do we make sense of this randomly distributed heterogeneous material? How can we make sense of it in order to use it as an engineering material in the sense of concrete or steel? And the whole process involves trying to find some common thread that links rocks together. And the next slide shows, and I apologize for the size of this, you have, there are only 3 figures in the paper in front of you, because I didn't want to include color, but I've added 3 colored pictures, which you'll see in the screens around the room. And this one shows a collection of several thousand tests on rock, on intact rock. These are tests where the rock is confined by oil pressure and loaded, so there'd be oil pressure around this, and loaded in an axial direction. And you determine, therefore, the triaxial strength of the rock. And by plotting all of those results together, it turns out that there is a common pattern. In this case, the lines that vary with size are the ratio of the tensile to compressive strength of rock. Obviously, you can imagine that a very brittle rock like a granite or porphyry would have properties like glass. It's very, very strong in compression, but very weak in tension. On the other hand, if you have a soft rock like a sandstone or a mudstone, the properties are closer together. And we can take it one further with the next slide, which shows that it's possible to have all rocks, the properties of intact rocks, fit on a single line. And this is the kind of commonality that I searched for, because we can now take that and say, although it's approximate and we know that it will vary from rock to rock and even from this meter to that meter of the same rock, nevertheless, there is a pattern there that we can use. And this formed the basis of the what later became known as the Hook-Brown-Thiele criterion, a methodology for establishing the strength of a rock mass, which you could then say, I can build a foundation or a slope or a tunnel in this, and I can anticipate certain properties, and I can determine what kind of steps I would have to take to ensure that this excavation is stable. And the next slide, which you have in the document in front of you, is one of the examples of the use of this technology. On the lower scale is the ratio of the rock mass strengths to the in situ stresses. Obviously, as you go deeper below surface, the stress on each element increases, and if you divide the rock strength by that number, you have the lower scale, and the vertical scale is the convergence of the excavation that you would expect for those conditions. And you'll notice that there is an asymptotic curve there, which we can use for anticipating the behavior of the rock. And the next slide, which you don't have in your handout, but which you can see in the screen here, shows a number of tunnels around the world where as the stresses relative to the strength of the rock increase, you have worse and worse conditions. So starting on the lower right-hand corner there is a tunnel in Greece where it's behaving very well, and it can be relatively easily supported by cables and rock bolts and steel girders. And then as you move up to the middle, you see a tunnel there in Taiwan where the roof of the tunnel, this is a 16-meter span highway tunnel, the roof has caved 1.5 meters, which is clearly unacceptable. So that becomes something you've got to deal with. And the worst case that I've ever dealt with is the case right at the top, which is a tunnel in Venezuela, which was 25 kilometers long, and it took 33 years to complete the tunnel because every time they tried to complete it, it failed. And you can see in the photograph, which is difficult for you to see, I admit, that in some cases the tunnel closed up completely. It was 5.3 meters in diameter, and sometimes there was no tunnel left. It had to be remined. And what we need is the ability to predict in advance whether we're going to have problems like this and make adequate plans to deal with them. Then we can handle the situation relatively easily. What we don't need in any engineering activity is surprise. We need to have some advance. And I hope that in the work that I've done, I've contributed towards this diminution of risk. And talking about risk, one of the things that we can do, although we know that rock is very variable, is to use what we call Monte Carlo analysis, which is effectively to say we have a range of properties for each element in the problem, and we will do a Monte Carlo analysis, which is effectively throwing the dice many hundreds of times, many thousands of times, until you see a pattern emerging, which gives you an idea of how that rock mass might behave in the real world. And that, I hope, is what I've contributed to this field, and which is the reason, presumably, why I'm standing here today to receive this degree for my contribution. And I'd like to conclude by thanking the rector and the university and all the individuals who were involved in making this possible, and particularly David Passerisa, who shepherded this process through its whole process. Thank you very much, and thank you all for this great honor.
Now we are going to proceed with the presentation of the Rock Science Prize by Dr. Parcerisa and Dr. Hoek. Dr. Parcerisa.
Bé, en aquesta cerimònia volíem tenir un moment especial dedicat als estudiants. Bé, han vingut aquí, a banda, evidentment, d'autoritats, professors i personal de la universitat, un munt d'estudiants. Estudiants que ens venen del grau en enginyeria minera, del màster en enginyeria minera que fem aquí a Manresa, però també estudiants que ens venen del grau en enginyeria civil, de l'Escola de Camins, o estudiants de geologia tant de la UAB com de la UB. I aquests són el nostre futur, i són els que han de tirar endavant amb els coneixements, entre d'altres, aportats pel doctor Evert Hoek. En aquesta ocasió hi ha hagut l'empresa Rock Science, que és una empresa de distribució de software relacionat amb l'enginyeria del terreny, la qual ofereix un curs intensiu de formació en el seu software i de manera gratuïta amb un dels estudiants que ha vingut aquí. La manera de triar-ho ha estat per sorteig. Tots s'ho mereixerien, però només ens ofereixen un curs. I per tant, l'altre dia, amb la comissió electoral que tenim a l'Escola de Manresa, vam fer el sorteig i doncs hi ha un guanyador o guanyadora que tot seguit el doctor Evert Hoek anunciarà.
The name of the winner of this competition is Moises Munoz.
Està fet amb la comissió electoral, però és estudiant meu.
Please. Now we are arriving to the end of this ceremony. Dr. Evert Hoek, Mr. Valentí Junyent, Major of Manresa, Ms. Rosa Argelaguet, Director of the UPC's Manresa School, Mr. David Parcerisa, Dr. Hoek's sponsor, authorities, UPC colleagues, ladies and gentlemen. Today we are gathered in this beautiful Manresa campus library to welcome Mr. Hoek to our UPC community. It is our greatest honor. We are in excellent company. Actors in the public life of the city have joined us for the final celebration of the school's 75th anniversary to thank a man who had led the way in aiding and transferring the results of research to the Manresa region. Thank you very much. It is the second time in the history of our university that an honorary doctorate award ceremony is held in Manresa. The first took place in 1992, when the award was for Mr. Jan Willem de Leeuw, whose sponsor was the Professor Xavier de las Heras, who is a member of this year's committee. I wish to thank the Professor David Parcerisa for delivering the oration and Dr. Hoek, an outstanding figure in mechanical engineering applied to rock behavior, for his speech. In my first year as the rector of the Universitat Politècnica de Catalunya, I have had the chance to come to Manresa a few times, often to pick up or celebrate some of the prizes awarded to the school for its long history, and of course to its dynamic academic community. Social actors in Manresa and the surrounding area have expressed an interest in the continuity of degrees that have a direct impact on the region, like automotive engineering or mining engineering, which in Catalonia is only taught at our university here in Manresa. To prove the importance of having specialized engineering in in these fields, today we have been given a true lesson. I hope I can apply this lesson to strengthen rock mass behavior, to secure the stability at our university management team. Thank you very much for your interesting advice. Dr. Hook is a much loved person on this campus and in Manresa. I have witnessed that myself, and I know that the school's members have worked especially hard, so I wish to thank them for making this event possible. We are delighted to add Dr. Evert Hoek to our university's list of honorary doctoral degree holders, and we hope that his knowledge and live lesson will inspire our students and teachers to keep working hard in full awareness of the impact that their knowledge can have to their immediate environment, to our cities, to our citizens. Thank you very much.